The goal of this lecture is to introduce deterministic finite automata. Let's start with an example. A deterministic finite automaton has states that will be denoted with circles. In this case, we have two states. We have also directed edges that connect states. Essentially, the picture corresponds to a directed graph where the states are the nodes and the edges are the transitions between states that are also labeled with symbols. Some of the edges may go from one state to itself. In this example, we have two edges of this form. Moreover, we have special states called accepting states that we denote with this cross, and also an initial state denoted in this way. An automaton is a model of computation that recognizes words. Let's see an example of execution with a possible input word. The inputs are the words built on the alphabet of the word recognized by the automaton. Initially, we see that the automaton is in the state marked as initial. It reads the first symbol and changes its state using the corresponding transition. In this case, after reading A, we jump to the second state. Now we read a B, and from the second state we go back to the first one. After reading another B, we fire this transition and stay in the same state. Then, with an A, we jump to the second state, and so on. With this B, we go back to the initial state, and finally, after reading the last A, we jump to the second state. Since this state is an accepting state, this word is accepted. The set of words accepted by this automaton, we can more or less guess it, are the words ending with an A. It can be written formally in this way. Usually, deterministic finite automata are described formally as a tuple containing a set sigma, the alphabet, q, the set of states, delta, the set of transitions between states, q0, the initial state, and f, the set of accepting states. In this case, sigma is the set containing A and B. The set of states, we call q0 to the first one and q1 to the second. We call the first one q0 because it is the initial state. As only accepting state, we have q1. The transition function is formally defined as a function that, given a pair state symbol, tells us in which state we end up after reading the symbol. In the case of q0 and an A, we go to q1. In a similar way, we consider the rest of the cases. Let's see another example. In this case, we'll write the language that we want to recognize, and then we'll think on how to define an automaton for this language. We are looking for an automaton recognizing words over AB with an even number of A's, which is denoted like this. We'll use two states because to recognize words with an even number of A's, at any point of the execution we need to remember whether the number of A's until this point is even or odd. The state on the left means that we saw an even number of A's, and the state on the right means that we saw an odd number of A's. For this reason, reading an A changes the state. The initial state will be the one on the left, because before starting reading the input, we saw an even number of A's. It is also an accepting state, because we want to capture the words that evaluate to this state. Reading a B makes us stay in the same state, since it does not change parity of a number of A's. Let's see one last example. We want now an automaton recognizing words over AB ended by ABA, which is denoted like this. The idea consists on using states that remember the last useful information until the moment while reading the input. In the initial state, we do not need to remember anything. But when we read an A, it is convenient to remember that the last symbol we saw was an A. If we read a B, we stay in the same state. From this second state, we are remembering that we saw an A. If we are in this state and we read a B, we have to jump to another state that remembers that we saw AB. It is convenient to give a name to the states denoting what are we remembering at each state. If from this state we read an A, we should remember that we saw ABA, and hence we create this state and this transition. If from the third state we read a B, we jump to the initial state, since nothing of what we remember is useful anymore. If from the last state we read a B, we should jump to the third state, since the last word seen that is useful to construct ABA is AB. Otherwise, if from the last state we read an A, only this A is useful to construct ABA, and hence we jump to the second state. The accepting state will be the last one, since it tells us that the last subword seen is ABA.